Hey there, this is Dr. Joseph. Today we're learning about derivatives of inverse functions. Our goal is to relate the derivative of an invertible function to the derivative of its inverse algebraically and geometrically. Then compute the derivative of the inverse of a function, given that we know the derivative of the original function. So, what does it even mean for a function to be invertible? It means there is another function called f inverse such that f inverse of y is equal to x exactly when f of x is equal to y. And so I don't want to complicate this too much, but that means f inverse of f of x is equal to x. And that's composing. And it doesn't matter the order I do that in, f of f inverse of x is also equal to x. Okay, so here is the main point for today. If f of x is differentiable at a point x, then the derivative of its inverse at f inverse x is equal to the reciprocal. This formula looks a little confusing. It's actually a very simple formula once you know how to apply it. So coming back to this point about when we compose f and f inverse, we get x. Where this formula comes from is applying the chain rule to this composition and then solving for the derivative of the inverse function. Anyway, let's look at a picture. Here's a nice invertible function, and here is its inverse. So graphically, the inverse function is obtained by reflecting over the line y equals x. And for example, if BA is a point on the graph of f of x, that means that AB will be a point on the graph of f inverse. So remember, the inverse function takes the output of f right back to the input that it came from. So we want to understand at a point, at an x value a here, what is the derivative of the inverse? And it's going to be related to the derivative, the original function, not at a, but at b, because BA is the point that corresponds with AB graphically after doing that reflection. So what that theorem says is that the slope you get here is just the reciprocal of the slope you get here. Another way to say that is when you multiply these two slopes, you get the number 1. So for example, starting off here, I have a pretty high, large slope for f. If I look at the corresponding point here, it's very small. So a big number has a small reciprocal. Then as this is getting smaller and down to 1, this one will be getting bigger until it gets up to 1, right? Because the reciprocal of 1 is 1. So at this point, they're both 1. And then now this one's getting bigger. So this one has to be getting smaller. And you start to get the idea. So to sum it up succinctly, the derivative is just the inverse, the reciprocal number. But you have to be careful to evaluate at the right x value. This one is at a, and this one is at b. Okay, so example 1. F of x is this degree 5 polynomial, and g of x is whatever its inverse is. So we're told that it exists, so we don't have to worry about whether or not it does, but using the fact that f of 1 equals 0, figure out what g prime of 0 is. Okay, so this means our point on the graph of f is the point 1, 0. And so on the graph of g, we'll have the point 0, 1. So this is that AB point we were talking about. So what that theorem says is that g prime of 0 is going to be 1 over f prime of 1. I have to switch my A and my B for the inverse function. So to figure out f prime of 1, I first need to figure out f prime of x. And that's not so hard. It's 5x to the 4th plus 6x squared plus 1. And now I evaluate that at 1. So I get 5 plus 6 plus 1 is 12. So my answer is that g prime of 0 is 1/12. All right, so here we have a drawing of the graph of a function f in red, and here is its tangent line in green. So first question, what is f inverse of 2? And part B, what is the value of the derivative of f inverse of x when x is equal to 2? So try that by yourself. The answer is 1 1/4. All right, so let's relate this to some of the derivative formulas we already know. The one I'm really thinking of is this first one. So the definition of natural log of x is that it's the inverse of e to the x. E to the x is this kind of a graph, exponential growth, that is invertible, and this is its inverse, so its inverse looks like this. So using that formula, let's check that the derivative of natural log x is what we told you it is. So the formula says I should do, let's write it down. Derivative of f inverse prime of x is supposed to be 1 over f prime evaluated at the point f inverse of x. So I'm evaluating this at x here. So on the graph of natural log, I have the point x ln x. This is my AB. So that means for this derivative, I'll want to do 1 divided by e. Well, so derivative of e to the x is e to the x. That's my f prime. And now the point I plug into e to the x is that corresponding point, the b to my a, right? So where this was x, I need to be plugging in natural log of x here. And what's e to the natural log of x? Well, because those are inverse functions, right? That's f of f inverse of x, that's just x. So this formula is the justification for why the derivative of natural log x is 1 over x. Going back to these inverse trig functions, their inverses are called arcsine, arccosine, arctan, also sometimes denoted like this. And on the left here are the derivatives of those three inverse trig functions. On the right are the derivatives of the other three, cotangent, secant, and cosecant. These are just here kind of for your reference. You do not need to memorize the three on the right here, but these three on the left are important. And those are going in your toolkit now. So you should learn these three formulas on the left for inverse sine, inverse cosine, and inverse tangent. You do not need to memorize the other three. It's a little bit harder to derive these three formulas than for e to the x and natural log. It's not crazy hard, but it involves a trig identity. So you might want to try that on your own. Ask your instructor if you get stuck. Those are good problems to work out as well. And that's all for today. Have a good one.